Okay, so today we are on 4.1, which is just the beginning of multiplying and dividing polynomials, which should be a review. Most of it will be a review for you. In the packet that I gave you, you should be doing the skills 8.1 and 8.2. In your book, it is 9-1. So, first I'm going to do a quick fraction review. You should be able to do all of these with no help from me, hopefully. So do them, come back and check your work. Okay? All right, so let's go straight through them. So 16/20 reduces to 4/5. 21/49 reduces to 3/7. 9/36 reduces to 1/4. 35/42 reduces to 4. Wow. Let's try that again, shall we? That reduces to 5/6. 27/30 reduces to 9/10. 14/22 reduces to 7/11. 24/48 reduces to 1/2. 12/27 reduces to 4/9. And 18/42 reduces to 3/7. Okay, so big part of rational expressions is fractions, being able to multiply, divide, add, subtract, and use common denominators. So if that's something you're shaky on, you better get really good with it really quickly. Go practice your bow tie method for adding and subtracting. That is in section, in the second section, adding and subtracting. So you also need to know how to obviously solve quadratic equations, which we've been doing for a long time. Just a little bit of a review. So you always need to have that set equal to 0. So you need to bring that 15 over. You would have x squared plus 2x minus 15 equals 0. Then you're going to factor and solve. It says find the solution. I'm expecting you to have x equals a number. We now know with polynomials, of course, that the number of solutions you have is always equal to the degree. So every quadratic equation has 2. So that would factor to x plus 5 and x minus 3. So our solutions would be x equals -5 and x equals 3. Number 11, even with inequalities, they end up being the same way. So you would still need to move that 15 over to the other side. It's going to look very similar to the problem we just did. So you'll have x squared plus 2x minus 15 is greater than or equal to 0. Factor both. To get x plus 5 and x minus 3 is greater than or equal to 0. You're setting those both now equal to, greater than or equal to 0, not just equal to 0. So x is greater than or equal to -5, and x is greater than or equal to 3. Okay. You should easily be able to factor all of these now, so go ahead and do 12 through 15, and then come back and check your work. So number 12, we have an x in each term. We need to factor out first, so we get x times x squared plus 11x plus 30. What's left in the parentheses, I can now factor down to x plus 5 and x plus 6. So we should have 3 solutions. I know that because it's a third degree polynomial. So one solution is x equals 0, one is x equals -5, and one is x equals -6. Those are our solutions for number 12. Number 13, same exact problem. The only thing different is now they have it set as an inequality greater than or equal to. So again, we're going to factor out the x, and the rest of it will factor out to x plus 5, x plus 6. Now the only difference is the inequality. So you have x is greater than or equal to 0, x is greater than or equal to -5, and x is greater than or equal to -6. Okay, last two, again, same problem, just different application, whether it's an equation or an inequality. So you need to bring this 39 to the other side by subtraction. So we'll get x squared minus 5x minus 36 equals 0. Then we need a factor, and that's x minus 9 and x plus 4. So our solutions are x equals 9 and x equals -4. Going to have exactly the same solutions on number 15. because it's the same problem. The only thing that changed is changing it to an inequality. Minus 36 is less than or equal to 0. X minus 9 and x plus 4. So x is less than or equal to 9 and x is less than or equal to negative 4. Okay, so now we're getting to features of rational functions, which means we are graphing. So you guys already know linear equations. Now you know all kinds of polynomial functions to graph. So now we need to get into rational functions. So the parent function for rational equations is f of x equals 1 over x. So now instead of x being a numeric value on top, it's going to be the denominator of our function. And it's got very specific features. So if we were to just make a quick table of values and plug in things that we normally plug in. So let's use -1. Sorry, let's make that a -2. -2, -1, 0, 1, and 2. And we plugged in those values to see what we get. So 1 over -2 is just -1/2. 1 over -1 is -1. 1 over 0, here's where this presents a problem. You can't have a 0 in the bottom because that is undefined. So what happens with a rational expression is that's where it creates what we call an asymptote. We'll talk more about that in a minute. So let's finish filling out our value. 1 over 1 is just 1, and 1 over 2 is 1/2. So let's go over to our graph and plot those points. So we have a point at -2, -1/2, -1, 1. 0, 0 does not have a point. 1, 1 has a point, and 2, 1/2. Oh, sorry, that should not be there. 2, 1/2. Okay, so what happens is at 0, this becomes our vertical asymptote. So right at this point, wherever the denominator becomes 0, that's going to be your vertical asymptote. So right here is kind of our imaginary line that our graph is going to come close to but never touch. And what ends up happening, it's kind of your parabola, but it's split into 2 pieces. It's going to look something like that. And that's the parent graph. Everything else is going to shift off of that graph. So you kind of need to know the characteristics of that. And your vertical asymptote is going to shift depending on how your denominator shifts. And that's going to be the opposite, just like it has been in a lot of our other functions. And for this one, actually, clean up my line a little bit here. This should come close to the x-axis, but not quite touch. So it should look more like this and more like this. Okay? So that's the parent graph. So all the ones that we have down below here are going to adjust a little bit just off of that. So for all of these, you can always do a table of functions, decide whether they are increasing, decreasing. Let's go back to the parent graph. So our domain is all x's except for 0. So our domain is all x's but 0, because that's where our asymptote is. And our range is all real numbers. Okay. So let's do the same thing for 16. So do a quick table of values, and let's just see what happens there. So you have the same function, the only difference is the number on top is changed to a 4. So let's go -2, -1, 0, 1, 2. 4 over -2 is -2. 4 over -1 is -4. 4 over 0 is undefined. This is our asymptote right here. 4 over 1 is 4, and 4 over 2 is 2. Let's go back over here, graph our points. So we have a point at -2, -2, -1, -4, 1, 4, and 2, 2. Our asymptote is still at 0 because nothing has shifted that denominator, so it's still going to be like that. But now our line is going to look something like this. It's just gotten taller and skinnier. Okay, it's shifted up off the x-axis a little bit, but a similar looking line. Okay, your domain is still all reals but 0, because 0 is where it makes that function undefined. So domain, let's get that one off of there. So your domain is all reals but 0. Range is all reals. Okay. So now let's see what happens when we have one that shifts our asymptote a little bit. So what's going to happen is, if you remember when we had, let's go back for a minute, when we had so let's go back to when we were doing exponential functions, and if we had something within the x, within the parentheses with the x, this was always an opposite shift, because it's whatever makes that value 0, what takes us back to x, so it's an opposite horizontal shift. If there was a number outside, that was a vertical shift, up or down. Okay, so same kind of shift happens here. So whatever number it's going to take to make our denominator 0, whatever gets x plus 5 to equal 0. So the only thing that you do there is you subtract the 5. So x at x equals -5. That would make our denominator value 0. So -5 is going to be your asymptote at that point. So x equals -5 is 1, 2, 3, 4, 5. It's going to be right here. That is your asymptote for that line. So that can also be your middle of where you plot your points for the table of values that you're making. So we'll go -5 in the middle, so then we'd have -6, -7, -4, and -3. That's what I would do. So you've got 1 over that value plus 5. So -3 plus 5 is 2, so that would give you a y value of 1/2. -4 plus 5 is 1, so 1 over 1 is 1. -5 plus 5 is 0. This gives you an undefined. That is your asymptote right there. -6 plus 5 is -1. 1 divided by -1 is 1. And -7 plus 5 is -2, so that gives us -1/2. Go over to your graph, plot those points. So you should have a -3, 1/2. -4, 1. And -6, -1. -7, -1/2. So your line is going to look, again, similar to the original one, except now it's shifted over to the left by 5, because it was an opposite shift of our 5 right there. You start to see that all the graphs that we do kind of have similar features and similar traits as far as how they shift. So go ahead and see if you can do 18 on your own. It's pretty similar to 16. You should be able to do that pretty easily. Think about where your asymptote is going to be, wherever that denominator equals 0. So graph that one and then come back and check your work. So if I were to make a table of values, I can see that this doesn't have any shift going on, so I know that my asymptote is going to be on the y-axis at 0, at x equals 0. So if I made my table of values, I would use my -2, -1, 0, 1, 2. So here's my asymptote at this point. 3 over -2 is -3 halves. 3 over -1 is -3. 3 over 1 is 3, and 3 over 2 is 3/2. Plot those points. So -2, -3/2, -1, -3, and 1, 3, and 2, 3/2 right about there. There you go. So that's what that graph should look like. Erase the bottom of it because I covered up my next problem. Okay, so 19 looks similar, but recognize that the number that's changing on the bottom is not in the denominator with the x. It is actually outside of that rational. So what's going to happen is the answer that you get here is then going to have an addition of 1. That is going to make our graph shift up by 1. That's going to be a horizontal shift. Excuse me, a vertical shift up. So let's go ahead and do a table of values. I do know that what you can do is you can first graph, this is kind of what we did with logarithms and exponential graphs, is that we would graph just this part first, and then we would add 1 to each of our y values. So you could definitely do the same thing here. So if I used -2, -1, 0, 1, 2. So -2 over -2 is 1, -2 over -1 is 2. Our asymptote is at 0. -2 over 1 is -2. -2 over 2 is -1. So for all of these y values that I have, now I need to add 1 to each of them. Even my asymptote. Okay? So, what it's going to do now, so my final table of values is going to look something like this. My x values aren't going to change. They're just going to sit right where they are. But all of my y values are going to increase by 1. So the black table of values is what we need to graph. So still going to have an asymptote on the y-axis. Still my asymptote. And then I will have -2, 2. Oh, let's get a bigger dot there. -2, 2. -1, 3. 0, 0, 1, -1, and 2, 0. So what that really did was it shifted everything up 1 also. So my new horizontal asymptote is going to be at 1 here. So you've kind of got two asymptotes going on. Normally your x-axis is your other asymptote, but now that you've got a shift, now you're shifting that up 1. So now that's going to be your other asymptote. So your line is going to kind of edge on both of those. So it's going to look something like this and something like this. So the green and blue lines are your borders. Your blue line would be your horizontal asymptote, and your green would be your vertical asymptote. Okay. I think that might be it for this section. You're going to have plenty of graphing practice in class. The factoring practice I don't plan on going over in class. I expect you to come in with that ability and then go to 4.2 for adding and subtracting.